Hello, I'm Dan Bowles, and this is the fourth video lecture in a series to teach the principles of our physical existence as presented in my book, Are We Just Bubbles? An Alternate View of Existence. In the last lecture, we discussed the concept of vacuum space bubbles and vacuum space pressure, and how an imbalance in the pressure around objects of matter cause the gravitational force. That same force as described mathematically by Newton in his law of universal gravitation. In this lecture, we will explore the other actions of matter as described by Newton's laws of motion. These actions of force against the movement of matter with mass by the vacuum space bubbles is commonly called the property of inertia. Although it is different than the gravitational force, it again is caused by an imbalance in the vacuum space pressure that is induced by forcing an object of matter to move through them. Newton's second law of motion states, it takes a force to change the velocity of an object with mass. Velocity is defined both by its speed and direction, and acceleration is defined as a change in the velocity of an object. So stated verbally, Newton's second law of motion says that it takes a force to accelerate a mass. Mathematically, it can be expressed as force equals mass times acceleration. It also takes a force to make an object go in a curved path instead of a straight direction that it wants to follow. This is because the direction of the straight path is constantly being altered when moving in a curved path. The constant application of force required to make a moving object travel in a curved path is also known as the centrifugal force. That is the force you feel if you swing a ball around on a string. To start, let's explore the action described in Newton's second law and see how the vacuum space bubbles can apply a force to an object being accelerated. It takes a force to change the velocity of an object in space. When I push this little truck, resting on this hard, smooth surface, I feel the resistance it offers when I start to move it. The faster I try to move it, the more force it takes. Also, if I add some weight to the little truck with these lead fishing weights, then it will take more force to accelerate it to the same speed as it was without the weights in it. Since I pushed the truck in a straight line, and the wheels are straight to make it go in a straight line, there's no centrifugal force felt on the tiny little passengers inside of it. An interesting thing, if I happen to be doing the same experiment on an airplane flying on a level path at a steady 600 mile an hour speed, I would feel the same inertial force as I did while stationary relative to the Earth. This is because the inertial force is relative to the change in speed versus just the speed itself. It would make no difference if I was traveling east, west, north, or south, or if I were in a spacesuit in outer space doing the same experiment with no Earth's gravity around. The inertial force would be the same as the force in a stationary Earth-based experiment. In this lecture 4 and in lecture 3, I deliberately not mention how an external force can be applied to an object to move it in space, and have highly simplified the illustrations so that the fundamental concepts of gravity and inertial forces can be easily understood. All of the physical objects that we normally encounter and can see with our eyes, like this rock, is a complex cluster of subclusters and clumps of space bubbles that make up the elemental atoms and molecules of matter. The components of atoms, the electrons, protons, neutrons, and even the subatomic particles, the quarks and such, are still just space bubble groups of different geometrical configurations separated by vacuum space bubbles. The only thing holding up the bubble groups together is the restriction of expansion the bubbles have on each other, imposed by the sharing of sides and the inability to share space. Since the void that our universe is sitting in is infinite, there is no special place in it for a location reference. It has no beginning nor an end, so there is no particular place for the universe to reside. Even if there was, the reference would always be moving as the universe expanded anyhow. But we really don't care where the universe is in the void. Since we are observing the actions of the universe from inside of it, with the vacuum space bubbles as a length measure, we can use the universe itself as a reference. The vacuum space bubbles, even though they are expanding at the speed of light into the void, appear fixed in size and stationary to us. Objects with mass can move in position relative to them. The vacuum space bubbles are the fabric of space and are the space-time medium that scientists talk about. Now, before I can explain the action of inertia, which is the force exerted on a mass by the vacuum space bubbles when it is moved in space, I am forced to introduce a new and an unexplored type of fluid dynamics. Traditionally, the study of the flow of fluids have only addressed those fluids which are compressible, like the gases, or the non-compressible ones, like liquids. The vacuum space bubbles are a special non-compressible expanding fluid that everything in our physical universe exists in. They are expanding and appear stationary in position, so exact details of how the vacuum space bubbles behave when a massive object moves through them is not precisely known. There really haven't been any occasions to study this in classical physics, and it would be a great thing for some energetic young student working on a PhD to explore. But for purposes of understanding inertia, I'm going to speak in broad and generalized terms of how this expanding vacuum space bubble fluid applies a force to an object with mass. Now, in describing inertia, I will also have to talk about proportional expansion of the vacuum space bubbles versus linear expansion of them. In order for objects of matter to appear constant in size and occupy a fixed volume of universe space, everything has to be invisibly expanding proportionally into the void. This means everything expands into the void by a certain ratio to its size. If a cubical vacuum space bubble, which appears constant in size to us, doubles its size in the void, then all sides of the cubes would be doubled. The diagonal across the cube would be doubled as well, but its linear expansion into the void length units would be greater than that of the sides because it was longer than the sides to start with. The only voluminous shape that expands proportionally and simultaneously linearly in all directions is a sphere. So for ease in understanding distortion of the proportional expansion of the vacuum space bubbles, I will represent them as spheres in the non-distorted condition. In the case where there is expansion distortion, they will be shown as ellipsoids. Again, I'm going to represent space in a two-dimensional model for simplicity and ease of understanding. The squares in this diagram represent the uniform distribution of vacuum space bubbles in universe vacuum space. They appear fixed in size and stationary to us, even though they are expanding at the speed of light into the infinite void. I have further simplified the vacuum space and represent the uniform expansion of the vacuum space bubbles first as spheres and then as circles in this 2D representation. Remember that the vacuum space bubbles are really cubes, and these circles represent the expansion only, not the physical shape of them. I have represented an object of matter as a polygon of compacted space bubbles so we can readily see the actions it has on vacuum space bubbles when moved through them. Remember that the bubbles are stationary and are a point of reference. Any action must be an object moving through them. When an object with mass, which is just a clump of condensed space bubbles, moves in a stationary vacuum space bubble medium, it causes the vacuum space bubbles in the path of movement to be restricted in their expansion. The bubbles resist by applying a force to the object in the opposite direction of movement because of this increased vacuum space pressure on this side. This force is seen as the inertial acceleration force described by Newton. Force equals mass times acceleration. Now I will mention that, as I said in Lecture 2, the visible energy that we can detect is caused by a change in the expansion rate of a group of space bubbles relative to its surroundings. These space bubbles had a change in their expansion rate relative to these surrounding ones. They were reduced in expansion. In this case here, we have stored the inertial energy of the moving object in the restricted vacuum space bubbles ahead of it. In the case where we would be slowing the object down, the stored moving energy, also known as the kinetic energy, would be released and exhibit itself in some fashion. Newton's first law of motion simply states a body at rest, or a body in motion, tends to stay at rest or in motion unless it's acted on by an outside force. If we apply a force and start this little car moving, it will keep moving in the direction you pushed it unless some force is applied to make it stop. Not stop there because of friction on the table. Now you might be thinking, what keeps the vacuum space bubbles from continuing to exert a resisting force against the object while it is in steady motion, while it's not being accelerated? Remember Newton's first law of motion? A body in motion tends to stay in motion unless acted on by an outside force. Why isn't the restriction of the vacuum space bubbles ahead of the moving object slowing it down as it moves through them? The answer is the vacuum space bubbles are displaced by the object as it flows through them. Then as the object passes by, the restricted vacuum space bubbles give the object a kick in the butt as they return to their normal, non-distorted expansion shape. When an object is moving at a constant velocity, the quantity of vacuum space bubbles and their degree of expansion restriction ahead of the object is equal to the quantity of vacuum space bubbles expanding to their non-distorted shape behind it. Therefore, there is no net force on the object due to the steady movement. If, however, the velocity of the object is changed at some rate, it is accelerated, in other words, the degree of restriction in the direction of the acceleration will be greater or less than the expansion behind it, causing the inertial acceleration force to be felt on the object. And so, this is the cause of the action on moving matter in accordance with Newton's first and second laws. A force has to be applied to a moving object to change its direction or speed. Otherwise, it will remain on its same path of motion. Ultimately, these forces and the force of gravity come from the expansive, creative force inside of each space bubble. Also, the kinetic energy of motion is the result of a change in the expansion rate and resulting volume change of the vacuum space bubbles relative to its surroundings. The kinetic energy is stored when their expansion is restricted, and the kinetic energy is released when they are increased back to the normal surrounding vacuum space bubble expansion rate. The vacuum space bubbles are unique and are the only non-clustered and least dense bubbles in the universe. They are the ones that have the maximum volume as compared with other clumped bubbles, are symmetrical, and are regular cubes throughout. Clumps of space bubbles that form matter with a property of mass can take on practically any shape, geometrical shape that has flat sides and volume. The number of sides the clump bubbles have and the bubble shapes can vary. They could be highly irregular and non-uniform throughout, but the basic requirement that all adjoining sides of bubbles must be coincident and in intimate contact with only one other bubble still holds. It is this requirement that causes the space bubbles to stay clumped together in an object, and is the cause of the distortion in the vacuum space bubbles around it. Any change in the shape of the object's bubbles, or the vacuum space bubbles, that results in a change of the volume to surface area ratio, which is also a change in the expansion rate, will be exhibited as a storing or releasing of energy in our universe. Any change in the bubbles that affect the overall linear expansion rate of a given volume of space will also affect the passing of time in that space. Now remember that what we think of as motion is very, very, very slow compared to the speed of light, at which rate the vacuum space bubbles are expanding. So the amount of time that it changes, if you reduce the expansion, is proportional to the ratio of the speed to the speed of light. And same with energy, the amount of volume expansion that you change would be very small to changing matter, for instance, into a vacuum space bubble, which would be a huge change in volume and a huge release of energy. This is the E equals mc squared equation that Einstein talks about. Any change in the bubbles that affect the overall linear expansion rate of a given volume of space will also affect the passing of time in that space. Vacuum space bubbles make up the bulk of our visible universe and are the fabric of space-time. Their invisible volume expansion into the infinite void is the dark energy of existence. The rate of volume expansion may not be constant throughout the universe. Vacuum space bubble linear expansion rate into the infinite void defines the passing of time and the speed of light. Vacuum space bubble expansion is the cause of all physical existence. Thank you for watching and listening.